Good morning, and welcome back to Aviation 2017, and this morning's keynote, Innovation in the Age of the Third Aerospace Revolution. I'm personally excited about this because of NASA Langley's role that you've just seen and what we've played over the past 100 years. Let me take this opportunity to thank the sponsors of 2017 Aviation, formed as you see behind me. Without these generous support of these companies, this wouldn't be possible. Whether you're in Denver or watching on the live stream, we're using the conference I/O site for speaker questions during the plenary. The URL is AIAA-CNF.io. And there you can submit questions and read the speaker bios. More information is available on page 3 of your program. Before we hear Paul Eremenko, the Airbus Chief Technology Officer, I'd like to take this opportunity to highlight the 100th anniversary of Langley. As you've just seen in the video, our center marks its centennial on July 17th. For 100 years, we've been pushing aerospace sciences forward through aerodynamic testing, crafting the advanced concepts of flight, and changing conventional wisdom about flight. I'm happy to report that this legacy of innovation lives on at NASA Langley. We continue to grow that legacy through work such as the Environmentally Responsible Aviation Project, which identified key technologies making air transportation more efficient by reducing noise, emissions, and fuel use. With our partners in industry and across NASA, we're merging innovations into integrated concept demonstrators and clearing paths for new X-planes, experimental demonstrating airplanes. For instance, we're working on a low-boom flight demonstrator that's called Quest, Quiet Supersonic Technology. The ultimate goal here is to bring back supersonic flight over land. It's incredibly gratifying to be a part of this effort with NASA and the Langley team. The future is unfolding right now. We're entering an exciting era, and I'm confident that the work happening at Langley Research Center will continue to help illuminate the way forward, just as it has in the past 100 years. As I'm sure Mr. Eremenko will describe, the confluence of emerging technologies has created a surge of intriguing opportunities in our industry. Aviation has never before seen a pace of technology and business evolution as rapid as today. And increasingly, our industry is driven by newcomers and by technologies developed outside of the industry. This is both a challenge and an opportunity, but certainly makes for the most exciting time to be in aviation since those early days of jet engines and before that, the Wright brothers. So now please welcome Airbus Chief Technology Officer, Mr. Paul Eremenko, to share how Airbus is leveraging this third revolution and shaping the future of flight.
Ladies and gentlemen, dear colleagues, good morning. It's an honor and a pleasure to be here to be able to address you. I started my aerospace career at MIT in the late 1990s after learning how to fly a single-engine Piper Warrior in the cornfields of Indiana. And I vacillated for the first 2 years at MIT between studying aeronautical engineering, electrical engineering, computer science, or becoming a bum, possibly. I think we've all been there. But for those of you who know MIT, after taking unified engineering my sophomore year, there was no turning back. And so with some trepidation, I went on to a career in aerospace. Now, the reason I hesitated was because the aerospace industry of the 1980s and 90s, and many of you here I think vividly remember it, was not exactly a hotbed of innovation. We still had the Space Shuttle, sure, and the Concorde, but both were 70s babies. The industry was not entirely devoid of innovation, I'm bound to say. We, after all, at Airbus pioneered fly-by-wire in the 80s. But a college graduate in aerospace engineering faced the very, very real likelihood of spending a third or more of his or her career doing detailed design on a widget version 1.0 that represented a very incremental improvement over widget version 0.9. And they might see its first flight a decade or so away. The joke was, fly before you die. I turned out to be among the lucky ones. My first job after grad school was at one of the handful, and I can literally count them on one hand, of aerospace startups that existed in the early 2000s. It was at Aurora Flight Sciences, and its founder and CEO, and our incoming AIAA president, John Langford, is actually here with us. Hi, John. We worked on drones, and boy, did I think that I had the coolest job in the world then. And I did. But as I reflect on it today, two things are striking. First, how different the employment prospects for a fresh aerospace grad are today. In the past few years, MIT Aeronautics saw about half of its graduates go to a non-traditional company like Amazon, Google, or one of the now hundreds of startups that are in our industry. And second, yikes, did we ever miss the commercial drone revolution? Right, John? Although obvious in hindsight, back then I could never have imagined in my wildest dreams that in just a few short years, a multi-billion-dollar market for commercial and consumer drones would emerge, and not from us, the disruptors of the time, but from the cell phone industry in Shenzhen, China. These are two small personal observations. I guess that each of you has similar reflections on the rapidly changing face of our industry. And I have come to see this as the third aerospace revolution, the first being, of course, the Wright brothers and the dawn of aviation, the second being the jet age of the 1950s. And in thinking about what this third one means for us and how we should react to it, I invite you to spend a few minutes with me this morning looking at some of the underlying fundamentals. First, some technology trends. On the vertical axis here, you have a generic measure of cost performance, so dollars per unit performance of some sort, plotted on a logarithmic scale. On the horizontal axis, you have time on a linear scale. Here's what a typical technology curve looks like on one of these axes. This is the famous Moore's law, which says that the number of transistors in an integrated circuit doubles every 18 months. And assuming a fixed size and hence cost for a chip, this means that the cost per transistor decreases exponentially. In fact, most digital electronics follow a similar technology curve, and so here you see it for volatile and non-volatile memory. Here it is for imaging CCDs. Here it is for wireless communications. And when you have this kind of rapid technological evolution across multiple different domains, some kind of convergence, something interesting, is almost bound to happen. And according to Clay Christensen's now classic theory of technological disruption, either you get a new low-end entrant into an existing product domain, or, as in this case, you have a new product that addresses an unmet, latent user need. And in this case, it was, voila, in 2005, the development of the first iPhone. Now, moving into a different technology domain, let's look at electrical. Electrical have followed their own exponential curve, albeit a less steep one than digital technology. Here is the evolution of battery cost performance in dollars per milliwatt hour. And here is another example, are photovoltaics. I won't belabor the point and jump straight to the punchline. The combination of increasingly efficient electrical components, together with the commoditization of sensors, such as gyros, accelerometers, magnetometers, GPS receivers, and cameras, through the staggering production volumes in the smartphone industry, enabled, by 2010, some new entrants into our own industry. They seem to be following Clayton Christensen's other modality of disruption, a low-end entrant into an existing product domain. And I'm talking here, of course, about drones and CubeSats. Few of us foresaw, I think, the shattering of the barrier to entry and the simple vehicle architectures enabled by cheap solid-state sensors and electrical rather than mechanical power distribution and control. And indeed, if you look here at the second vertical axis on the right, you see the number of new entrants, the number of startups in core aerospace domains like flying vehicles, satellites, launchers, et cetera, skyrocketing. At Airbus, we're tracking well over 200 aerospace startups today. And these startups have attracted over $5 billion in venture and private equity investment between 2010 and 2015 alone, which puts this ecosystem on par with many traditional aerospace companies' investments in new product R&D. And lest we fall into the classical fallacy of dismissing low-end disruptive entrants as toys, here are some examples of the kinds of products that this aerospace startup ecosystem has been working on. Some of these, like the SpaceX Falcon 9, have already eviscerated the markets of industry incumbents. I won't point any fingers. Others, like consumer drones and personal air transportation, are facing regulatory hurdles, but also applying immense pressure on the regulators to enable them to succeed. And perhaps most interestingly for us at Airbus, we see a group of new entrants that are increasingly targeting commercial aviation with electric, supersonic, and other technologies. But let's go back to our tech trends for just a minute. We talked about the technology curves for digital and electrical domains, and these have already begun a revolution in our industry. But I think that we have something bigger yet in store in the very near future. I'm talking about the ability to manipulate matter, or in other words, the ability to design and create new materials and structures with ease and flexibility of writing a software specification. These are technologies like reconfigurable manufacturing robotics, direct metal 3D printing, and even the ability to create new materials and structures using biological synthesis, directly programming the genome of organisms needed to produce them. These and other technologies give us mastery over the creation of the physical product, could well lower the barrier to entry to aerospace even further, and lead to opportunities for disruption that will be obvious in hindsight, but that we cannot yet grok. But the aerospace industry itself is not exactly chopped liver when it comes to innovation. We mastered the large-scale application of carbon fiber composites. We perfected energy extraction from gas turbines. Heck, we invented the gyros, accelerometers, and GPS receivers that came back through the somewhat circuitous route of the smartphone to disrupt us. So if we put aviation technology at a macro level, represented by transport efficiency, or dollars per passenger kilometer, into the same framework as before, we too have followed an exponential technology curve, albeit a somewhat shallower one. So let's review. If you take aircraft all the way back to the Wright brothers, the doubling time, or the slope of the exponential, is around 30 years. In other words, it takes 30 years to double the transport efficiency of commercial aircraft. This corresponds to an average annual improvement of about 2–2.5% per year. By contrast, new direct manufacturing technologies have a cost-performance doubling time of 5 to 7 years. Electrical technologies, 3 to 5 years, which is about 10% year-on-year growth. And digital technologies, 18 months, and in some cases, much shorter than that. So this poses two principal challenges to us in the aviation industry. First, we are the stewards of a finely honed innovation machine, yielding products that are remarkably safe and reliable. Products that, and I can claim this without too much risk of hyperbole, I think, have really transformed human civilization over the last century. How does this innovation machine grapple with an emerging technology landscape that is moving at a clock speed that is an order of magnitude faster? And the second question is, we're used to being the masters of our technological destiny, to being the drivers of key technologies needed to make each successive generation of our products. And suddenly, we find that consumer electronics, automotive, and other industries outspend, outpace, and out-innovate us in digital, electrical, and manufacturing technologies. My boss, the Airbus CEO, Tom Enders, spoke at this very podium at Aviation 2015, 2 years ago. His talk was titled, "Are we moving fast enough?" And you can imagine what answer he proffered to that question. I started at Airbus just a few weeks before Tom gave that speech, in which he said, "When we launched Airbus back in 1969, we weren't just bold. Some would say we were downright rude. And it worked. This industry needs to recapture that pioneering spirit. to find ways to work with new, audacious partners. And so, over the past 2 years, this became my mandate and my marching orders, to transform the way we approach research, technology, and innovation in a company that today is the world's leading seller of commercial aircraft, the world's largest producer of civil helicopters, and a top supplier of communication satellites. And so I'd like to share with you today our approach and to give you some concrete examples of what we're working on. At the core of everything we do is, of course, our company strategy. This includes our product policy as well as strategy for creating new products, new services, and new business models. Linked to the strategy, we have built a set of technology roadmaps. These are not just chronological buckets of activities, but a decision framework by which we prioritize technology investments, evaluate make versus partner decisions on particular technologies, assess the return on investment and the risk level associated with particular technology investments, and of course construct our operational planning and our budget. Now, let me say just a few more words about this technology road mapping methodology because it's absolutely central to the rest of the setup. We've organized the roadmaps in a 4-layer interconnected tree that you see on the left, starting with system of systems at the top, products and services, subsystems, and component technologies at the bottom. The purpose of this ontology is to identify highly connected roadmaps that are enabling to many others, and to compute the return on investment of roadmaps corresponding to activities that we don't directly monetize. So for instance, we as Airbus are not in the battery business, but we might leverage battery technology in numerous subsystems and products, which is where we would derive value from an investment in battery technology. Each roadmap is structured to answer 4 questions. First, where are we? We construct a set of Pareto frontiers representing the state of the art across key physics and economic-based figures of merit. Second, where could we go? This is a question that we answer using a concurrent design methodology. Basically, rapid, low to medium fidelity design trade space exploration to assess different technology insertion scenarios and what they enable. Third, where should we go? The prioritization of different technology scenarios, balancing risk and value, and taking into account what our competitors might do next. And lastly, each roadmap captures where we are going, providing an assessment of how our technology portfolio is balanced and its overall risk profile based on the variance and covariance contributions of the individual technology investments. From the roadmaps, we derive the portfolio of research and technology, we call them R&T, oddly, projects to pursue in order to deliver on the strategy with a given risk profile. We've evolved our R&T project organization from a traditional linear development model, basically a research lab with many hundreds of small projects driven by technology readiness levels, or TRL, and maturity gates, towards one that focuses on larger scale demonstrations of bundles of technologies, embraces agile development methods, and is organized through empowered teams. In addition to R&T projects, we've also created a new organization responsible for flight demonstrators. We modeled it on DARPA's X-Plane office and Google's Advanced Projects group, borrowing from them 2 key principles. The first is optimizing for speed. To that end, we started with a clean sheet approach to all internal processes, which frequently drive the clock speed of an organization. So we've redrawn procurement, HR, and other workflows from scratch, adhering to tenets such as single point approvals, risk management rather than risk minimization, and individual empowerment and accountability. We also use speed as a mechanism to incentivize risk tolerance. One of the challenges that we face at Airbus, and which I guess many of you find familiar, is the bleed over of the zero risk culture that our product engineering organization very rightly takes in designing products that are extraordinarily safe and reliable. But the bleed over of that into research and innovation, which can and should take risks, fail fast, and celebrate those failures. Speed is one of the most effective levers to promote risk tolerance among our researchers and technologists. When faced with a slightly impossible time constraint, the team is far more prone to take a moonshot. And every so often, they'll make it. And even when they don't, they will usually go farther than they would otherwise. The second principle underpinning our flight demonstrator organization is that of openness. This is both an internal culture of transparency and unsentimental data-driven decision-making, and also openness to working with the outside ecosystem. We exercise an aggressive make versus partner philosophy that compels the teams to work with best-in-class external partners in each technology domain as identified by the roadmaps. Working with non-traditional partners has forced us to develop a set of flexible mechanisms that make these engagements as fast and frictionless as possible. These include click-through contracting, for instance, or a startup-friendly intellectual property posture, plain language templates and framework agreements with leading universities around the world. And here, again, it's important that we optimize not for zero legal risk, but for speed of execution and for freedom to operate. The goal of flight demonstrators is to provide a rapid maturation pull, as well as a definitive measure of technology maturity, far more convincing than TRL. And this is for those technologies that pose a particular integration or industrialization risk, or where the effects of the flight environment cannot be adequately simulated on the ground. And I'll give you some examples in a minute. One important byproduct of building frequent flight demonstrators, by the way, is the motivating effect that it has on engineers and technologists. It's a tool for attracting top talent and an essential one for us to compete with the startups, the Googles, and the Amazons of the world. So the bulk of our research and technology investment is in these two activities, R&T projects and flight demonstrators. They're there to make progress on the technology roadmaps and build the future of the core business. We also spend a fraction of our resources hedging against disruption. Or to put it another way, trying to disrupt ourselves, and y'all, by the way, before someone else can. To this end, we've set up two innovation centers, one in Silicon Valley and one in Shenzhen. Shenzhen, by the way, is often referred to as China's Silicon Valley, but I think that vastly undersells the ecosystem. It's the fastest and most dynamic hardware ecosystem in the world today. The innovation centers operate on a very long leash. They pursue projects that are meant to be disruptive to the core business. This can be products, services, or business models. In essence, their charter is to think orthogonal to the roadmaps. And we view this as an insurance policy, as a form of technology hedging. It's also an avenue to capture top talent from non-traditional sources and geographies. In addition to trying to disrupt ourselves, we also want to identify and opportunistically engage external disruptors as early as possible. To that end, we created a network of startup accelerators called the Airbus Biz Labs. And we also stood up a venture capital fund, Airbus Ventures, which focuses principally on seed stage and Series A investments into aerospace and aerospace adjacent domains. One of the unique attributes of the Biz Labs is that they are the world's first and only, as far as I know, aerospace accelerator, meaning utilizing a hybrid model, meaning that they seek both external startups and internal Airbus teams to incubate there. It creates some very interesting cultural cross-pollination. And as for Airbus Ventures, we have likewise pursued a sort of hybrid model with it, setting it up as an arm's length, highly independent, financially driven investment vehicle, but with a focused investment thesis that ensures strategic alignment and engagement opportunities for portfolio companies with the Airbus community. And of course, across all of our activities, we try and share a common set of enabling infrastructure, like a technology scouting network, a cloud-based knowledge management system, and an intellectual property team. At Airbus, we view ourselves as a global company. For sure, we have European roots, but today we assemble A320s in China and in Alabama. We build helicopters in Brazil and in Mississippi. We just, together with our partners, opened the OneWeb satellite factory in Florida, and we have engineering centers spanning Bangalore, Beijing, Moscow, and Wichita. We have applied the same globalist philosophy to our research, technology, and innovation footprint. Most of the R&T and flight demonstrator activities are concentrated around major industrial sites in Europe to maintain critical mass and proximity and linkage to the business. But I mentioned also our innovation centers in Silicon Valley and in Shenzhen, and we've created a technology scouting network spanning the top innovation hotspots globally, including Israel, Japan, and India. So enough. This is how we operate. Now I would like to share with you some examples of what we're working on. I call this technology porn, that part of my talk. So first, let's talk about electric flight. As with many innovations that ultimately go on to change the course of history, electric flight began humbly with a small French home-built airplane called the Colombin Cricri. In 2010, we sponsored the development of an electric variant of the Cricri, replacing the two single piston, believe it or not, 15 horsepower engines with 4 small electric motors. With less than 30 minutes of endurance, it had rather limited utility. But it was an important existence proof and the beginning of our electric flight journey at Airbus. We followed the Cricri by a record-setting long-endurance flight of an electric motor glider called the E-Genius, which was able to cover a distance of 400 kilometers in 2.5 hours. By 2013, we were ready to take the next step. From a battery-powered all-electric airplane, inherently limited by the energy density of batteries, to a hybrid electric architecture, which, much like your Toyota Prius out there, still relies on the combustion energy of hydrocarbon fuels, but combines it with the flexibility of an electric propulsion system. So in 2013, together with Siemens, we flew the first ever serial hybrid airplane, the E-Star. It had a 30 kilowatt internal combustion engine running at constant speed, and a 70 kilowatt electric motor powering the propeller. And this, by the way, highlights one of the key advantages of a hybrid electric architecture: the ability to downsize the power generation capacity for cruise while augmenting it with stored electrical energy for takeoff and climb. The E-Star was followed by the E-Star 2, which introduced an integrated drive system, significantly improving the power-to-weight ratio of the hybrid electric propulsion system. Our latest set of demonstrators to fly have been the EFAN 1 series. The EFAN 1.0 and 1.1 further improved the efficiency of electric flight with a purpose-built aircraft. It successfully flew across the English Channel last year on the anniversary of Louis Blériot's historic first such crossing. Last year, we also exhibited at Oshkosh the EFAN 1.2, a series hybrid variant with a single motor generator powering 2 electric fans. Today, our partner, Siemens, is flying an aircraft that has nearly 10x the power level of all of its predecessors. The Extra is a high-performance aerobatic airplane modified to fly with an electric motor delivering 260 kilowatts of power in a 50-kilogram package. That's a 5x improvement in power density over the previous generation of motors that I just described. Just this past December, it set a world record for fastest climbing airplane in its class. Last year, we also formalized a major joint investment between Airbus and Siemens into a ground test facility called the Electric Aircraft Systems House located in Munich. This will be our primary development laboratory for electric propulsion technologies, and it's spec'd to be able to test power systems in excess of 20 megawatts, so you see a little bit of what's coming. Later this year, we anticipate setting another major milestone. It is the first hover flight of the Vahana. The Vahana is a single-passenger, all-electric, fully autonomous vertical takeoff and landing air taxi demonstrator. It uses 8 electric motors and a tilt-wing configuration to enable both hover and cross-city range on battery power alone. Vahana is one of the pillars of our urban air mobility portfolio, which I'll come back to a bit later. The Vahana relies largely on off-the-shelf electrical technology to get to a demonstrator rapidly. City Airbus, on the other hand, is a much larger 4-seat, also all-electric VTOL aircraft that is the flagship of our urban air mobility portfolio. City Airbus aims to push the state-of-the-art in power system density, which is being developed in the E-Aircraft Systems House laboratory. We anticipate first flight of City Airbus to take place next year. Now, we spoke earlier about the steep technology curve in electrical power systems, and a few years ago, the state-of-the-art in flight weight components was measured in the tens of kilowatts. Today, it is in the hundreds of kilowatts, and we believe that with a strong push, we could demo a 2-megawatt flight weight hybrid electric power system in about 3 years. We're calling it the EFAN X, and this would be a flight demonstrator on the scale of a commuter jet, where we would replace 1 or 2 engines with motors driven by an integrated turbine generator in the fuselage. In other words, it's a serial hybrid architecture again. Now, why 2 megawatts, you might wonder? We're not really in the regional aircraft business as Airbus. We see this as the upper limit of what's attainable with more or less conventional power distribution technology, without having to master superconductivity or other exotic approaches to power distribution. So we see it as a logical demonstrator to retire the integration risks associated with a serial hybrid architecture at this scale. These integration risks are things like thermal management, electromagnetic interference, arcing, partial discharge, and radiation effects on high-power electrical systems at altitude. Of course, the ultimate prize for us is to enable a hybrid electric propulsion architecture for a single-aisle aircraft at the scale of an A320 family. This takes us into the power range of around 20 megawatts for cruise and 40 megawatts of max power. So it's another order of magnitude or so over the EFAN-X. Now, mindful of the Malthusian fallacy of predicting the future based on an extrapolation of an exponential trend more than a few years out, I am reluctant to put a date on such a demonstrator, much less such a product. But it's becoming increasingly clear that such an aircraft is not only feasible, but actually desirable. Just to make sure that we're all on the same page here, a hybrid power chain today is less efficient than a conventional gas turbine engine. It includes the additional steps of converting to and from electrical energy. So for it to make a desirable product, we must eke out efficiencies in other areas. I mentioned one, enabling us to downsize and optimize the turbogeneration capacity in the aircraft for cruise, which is roughly half the takeoff power. But of course, this requires batteries or other forms of energy storage for takeoff and climb. And so the major source of efficiency comes not there, but at the overall aircraft level, simplifying the onboard systems and enabling fundamentally different aircraft configurations. For the first time since the jet age of passenger aviation began with the de Havilland Comet, we're really thinking about opening up the design trade space beyond the tube and wings configuration. For me, and I suspect for many aerospace engineers out there, this is a tremendously exciting prospect. Hybrid electric propulsion enables us to think about distributed thrusters, for instance, creating a blown wing effect that could allow shrinking the wing area, or using differential thrust to control the yaw of the aircraft, reducing the vertical tail surface, or boundary layer ingestion to re-ingest the wake at the tail of the airplane, cutting the overall drag by up to 10%. What you see depicted on the screen there is a concept resulting from a joint study we did with Rolls-Royce called eThrust. It is by no means a finished aircraft design. We have some years yet ahead of us. I think they're measured, and this is a prediction that I am willing to make today, in the single digits years. And they will be some of the most exciting aerospace engineering work in a half century. Now that is an aerospace revolution I'm willing to sign up for. Now let's move on to a different example. Let's talk about the in-flight passenger experience. To be frank, it isn't too much different than what it was in the early days of aviation. Yes, the seats are a little bit more ergonomic, and yes, you might get a personal TV in the seat in front of you nowadays. But the fundamental experience is still that of being strapped into a chair and being immobilized for hours. And of course, we work closely with airlines to make it as pleasant as possible, increasing the air density and the humidity in the cabin, making clever use of lighting to help with sleep cycles and in-flight passenger connectivity. But these are all relatively incremental changes. And the airlines face a conundrum. Most passengers treat their offering as a commodity and always select the cheapest flight, pretty much irrespective of the in-flight experience or the amenities offered. So they operate with relatively thin margins and tend to optimize for passenger density, not a differentiated experience. Now, I must caveat that I'm generalizing grossly here. There have been numerous exceptions, not the least of which is our own A380, which has developed quite a loyal fan following and has allowed its operating carriers to really differentiate their services. But what I want to share with you today is a disruptive rethinking of the passenger experience coming from our Silicon Valley Innovation Center, A-Cubed. And so there, we recruited some talented user experience designers from outside the aviation industry, mixed them with some of our top talents from our cabin engineering center in Hamburg, and posed the question, what would a clean sheet rethink of a passenger experience look like today? So they came back with a few observations. First, the cabin represents not just a means of transporting butts and seats, but a parcel of ultra-premium commercial real estate with a captive, upwardly mobile audience of prospective consumers. Second, what the airlines actually care about is revenue margin per flight, not dollars per seat mile. This dollars per seat mile metric has become a proxy for the profitability of an aircraft, but it inherently biases decisions towards cabin densification rather than maximizing passenger value. And third, a major obstacle to cabin innovation is actually of our own making. The increasing complexity of the cabins, such as wiring for in-flight entertainment, more sophisticated galleys, etc., has led us to optimize the airframe structure for specific cabin layouts. This makes retrofit of a new cabin configuration expensive and time-consuming. So the team proposed a concept we call transpose, creating a super flexible cabin experience using loadable cargo modules together with a freighter airframe. A carrier operator would choose which modules to load on a particular flight based on the duration, destination, and passenger demographics, or even expressed passenger interest. So you could imagine, for instance, on a long-haul flight, pre-reserved or on-demand accessible sleeping berths providing darkened, soundproof, climate-controlled environments. Think Fifth Element, for those of you who remember it. They would be available for, say, $50 an hour on top of your coach-level base fare. Would you use one? Or a casino module on a flight to Vegas, or a daycare module on a weekend flight that has lots of families with children. Premium retail, more like a Fifth Avenue outlet than a duty-free catalog in your seat pocket, could also make sense on some routes. The goals of transpose are to give the carriers the flexibility to experiment, to precipitate a vibrant passenger module innovation ecosystem, and to solve the requisite airport infrastructure and certification topics. So in the first year of the project, the team built a full-scale A330 freighter mock-up in a San Jose strip mall in which to test various modules and to perform some user testing. They developed a module architecture that provides all of the necessary interfaces and safety features while minimizing the weight penalty for modularity. And critically, they have ensured compatibility with existing airport handling and cargo loading systems, including an innovative air cushion-based cargo loading approach that makes it easy for a small crew to install a new module in less than 15 minutes. The past few months, the team has been doing simulated passenger testing with the aim to build a detailed economic model that encompasses passenger behavior and willingness to pay, as well as the business case for each segment of the industry value chain. So far, the results look promising. So the next step, hopefully a flight test. Now, the last example I'd like to share with you this morning is not about large commercial aircraft. It's about the future of vertical flight, and maybe also the future of our cities, by the way. Now, I firmly believe that opening the third dimension, the vertical axis, if you will, for travel in our increasingly congested urban areas is an inevitable future. While Elon Musk somewhat inexplicably prefers to burrow underground, I am far more excited by the prospect of a clean, quiet, and safe VTOL flight. When Igor Sikorsky developed the first commercially produced helicopter in the 1940s, helicopters held that promise. However, the reality is that while helicopters found many niche markets, they've never had much success in cities. I think this is mostly because of their appearance, a bit aggressive, and noise. They create a perception that there is a safety issue among the public. As in other aerospace domains that we discussed today, in VTOL, we stand at a convergence point of several new technologies, namely autonomy, electric propulsion, low-cost mass-manufactured composites, such as the BMW i-Series, and the digitally enabled business model of on-demand personal mobility. And I guess Mark Moore from Uber will talk about that a bit later in the week. Combined, they seem to offer the realistic prospect of a new class of vehicles that could make the dream of urban air mobility finally real. The hurdles we see are less about technology and business model, although for sure this domain challenges our existing model as an aircraft OEM. They're more about urban integration, public acceptance, and automated air traffic management. This is why we are embarking not just on the development of a city Airbus or a Vahana vehicle, the two that I mentioned previously, but rather on a journey to make an integrated urban air mobility solution a reality. So I won't say too much more about the vehicles, except that for us as technology demonstrators, they're really designed to span the trade space of enabling technologies and missions. So the City Airbus, which has flown a subscale model and has completed extensive full-scale rig testing, will be an optionally piloted four-seater, building up a more incremental approach to autonomy, similar to what Tesla is doing with the Model S autopilot. Vahana, on the other hand, is our tilt-wing single-seater. It has likewise flown a subscale model and is on track for first hover tests later this year. Now, being a single-seat vehicle, Vahana takes more of a step-change approach to autonomy, analogous to what Google or Waymo did with its self-driving car. So a lot of that project is focused on sense and avoid technology that needs to be at least as good as a VFR pilot, but likely far more reliable. Now, we also anticipate a potential cargo variant of the Vahana, about 100 kilograms, not bad, for large package logistics missions in urban environments. And speaking of packages, we've also been working on a smaller multicopter called Skyways, together with an integrated ground infrastructure for package pickup and delivery. We will be testing Skyways in an operational environment on the campus of the National University of Singapore later this year. But like I said, it's not just about the vehicles. It's about the integration with the urban environment and the user experience. And on this latter front, we've been testing an on-demand, end-to-end urban transportation solution called VOOM in Sao Paulo for a few months now. Sao Paulo is one of the most helicopter-friendly cities in the world, and we've developed a mobile app-based service that enables the dispatch of a helicopter together with a car service for the first and last mile of the trip. It's a single, seamless, on-demand transaction. As a result of VOOM, we have seen a 5x increase in the utilization rates of our helicopter fleet in Sao Paulo, and a dramatic expansion, a democratization, if you will, of the helicopter customer base. VOOM, of course, is great for our existing helicopter business, but more importantly, it is a significant step towards an on-demand, shared fleet business model for urban air mobility. It has helped us to understand the nuances of the passenger experience in this context and to gauge the economics of the market. This has given us greater confidence in the viability of urban air mobility as an end-to-end, city-by-city transportation solution. Now, again, I'm reluctant, if you've noticed, to predict the future. I much prefer to imagine it and to help build it. We're still in the early stages of the urban air mobility journey, but I would be astonished if in the next 4 to 5 years, we did not see the first full-scale pilot of an urban air transport system in a major city somewhere in the world. And I sure as hell want to help build it. So I hope that I've persuaded you that we are, in fact, in the midst of a third revolution in aerospace. Personally, for me, not a day goes by without thinking how grateful I am to be working in this industry at this very moment in time. We have a really remarkable confluence of technologies and business opportunities matched to great societal challenges. This is a chance not just to influence, not just to leave a mark, but really to imagine and build the future of flight together. Thank you very much for your attention, and I look forward to your questions. All right, so cellular data account. You are not signed up for a data plan. Okay. So I take the questions more or less in rank order. So everyone seems to know that we aren't moving fast enough, but we never seem to speed up. What are the actual bottlenecks? Well, you know, it's a good question, and I fully share the observation, and I think I tried to answer from an Airbus perspective, because it's nice for us to get up at each of these conferences, right, and lament about the fact that the traditional industry is moving too slowly and that we're being outpaced by the new industry. And so this is why I probably bored some of you with the litany of internal, some of them very process-oriented things that are the kinds of things that set the pace of innovation in companies. A lot of it is driven by process. A lot of it is driven by how we whether we trust our people, whether we're willing to take bets on humans, bets on people. And I think some of it is also driven on by the inherent risk aversion of engineers. And so I gave you some very concrete examples, I think, in my presentation of things that we're trying to do to overcome this process viscosity, procedural viscosity in a large organization, and also to change the incentives for our engineers to be able to move faster and to take the kinds of risks that you can take in a startup, but historically cannot take in a big company, particularly in a safety-critical industry like ours. Which disruptive aerospace innovators does Airbus most admire, and which ones are your biggest threats? Well, you know, I don't like to think of it in terms of threats and opportunities, because I think that every company out there, every innovator out there can be a threat or they can be a partner. And certainly, again, I gave you some examples. I was pleased and astonished both to see just this year a number of new entrants, Zunum and Wright Electric, that are aspiring to actually disrupt and beat the incumbents to market in electric commercial aviation. I think, of course, it's a threat, but also I think it's tremendously exciting. I think clearly SpaceX has already disrupted our Ariane business and has caused us to significantly restructure it and embark on a new generation of Ariane rockets. So I think in every domain there is a potential disruptor, but it's also a potential opportunity. What are the respective roles for government and industry in the fast-paced third aerospace revolution? That's an interesting one. You know, and particularly coming from a European company, and a company that not so many years ago had very active involvement from the governments of our European home nations. I think the role of government investment in this space is incredibly important. The challenge that we face, and I know that this is true on both sides of the Atlantic, is the tendency of government involvement in a space to actually slow it down, right? So we give you money, but it's in exchange for an extremely slow procurement process, a bunch of constraints and strings that come along with the funding. So I've actually been on a crusade with all of our government partners in Europe, but I think I would echo the messages also to government partners in the US, many of which we work with also, about the fact that you all need to streamline your processes, take a risk managed rather than a risk mitigated or a risk minimizing approach to engaging with industry. And I think that there are examples of this, right? I mean, if you look again at just to come back to the SpaceX example, I think ultimately what made SpaceX successful was as much Elon's and Gwyn's personality, as well as NASA willing to take a bet with a Space Act agreement going outside of a standard FAR acquisition framework, and pick SpaceX and fund SpaceX to be able to get to flight and to be able to get to the station. So I think those kinds of government involvements are absolutely critical. But I think the government partners also have to rethink their clock speed and the way in which they approach risk and the way in which they engage with industry. What fraction of Airbus's R&D budget is spent on truly new innovative technologies versus incremental improvement programs for existing products? Well, you know, it's I'm not going to get into budget figures, specific budget figures, obviously, but it's cyclical. And we go through product development cycles where we invest very heavily in the development of a new aircraft, and then we go through cycles of improving and doing incremental improvements to the existing product family. So there's quite a bit of oscillation that happens, and I think right now we are embarking in a number of new areas. So it's a particularly exciting time, and I think you see commensurately us focusing more of our attention on new products, and not just in the large commercial aircraft space, but across the board. Is it realistic to expect to work on the same timescales seen in consumer electronics when safety is so much more critical in commercial aviation than in the consumer electronics market? It's a very good question, and I think that it's a foregone conclusion in all of these conversations that we have to continue to make products that are extraordinarily safe and extraordinarily reliable. That's not a negotiable point. That's not a tradable parameter for us. That said, I think that there is certainly a propensity in my company, and I suspect a propensity in many of your companies, to hide behind the certifiability and the regulatory regime in order to not innovate, and to use it as an excuse to say, we'll never be able to certify that, so we shouldn't bother doing it. And I think that if you actually look at the history of the regulators, in most cases, they're there because they want the industry to thrive and to be successful. They're not there to stifle and suffocate the industry. So I think that there is a right way and a wrong way to work with the regulatory and certification regime. And I think that if you bring them along for the journey, you engage them at the innovation stage rather than creating something, bringing it to them and saying, here, please certify it. I think that that's a healthy and constructive way to engage with the safety authorities. And I think that you can have both. I think you can have innovation and speed and extraordinarily safe and extremely reliable products. Again, you look at in a different industry, but by analogy, you look at Tesla. Tesla is widely viewed and widely rated after extensive testing as one of the safest cars on the road, but is created in an agile, startup, risk-tolerant environment. So I think we need to be careful. Of course, we need to recognize the fact that safety is immutable, is an immutable parameter for us, but at the same time, not hide behind it in order to innovate less. I'm skipping ones, by the way, that either I feel like I've answered or that I don't know the answer to. Do you foresee a strategy for certification of urban flight systems, and wouldn't it be a major bottleneck? And so I think this is a nice continuation sort of my previous answer, which is, yeah, today there's no clear regulatory framework for electric VTOL. There's no clear regulatory framework for autonomous operation over urban areas, and there's no clear way to integrate autonomous systems into the air traffic system and the air traffic flow. So is that a reason for us to give up? No, I don't think it's a reason for us to give up. It's a reason for us to systematically engage with the authorities at the local level, at the state level, at the national level, at the international coordinating level, and try and come up with solutions. And we've been doing that. I know some of the other players in the room here have been doing that as well. And I think the reception largely that we get is a positive reception. Yes, I think there are things that we need to solve. There are issues that we need to address. But these are, in my view, solvable problems. So I don't see, I see it as a potentially gating factor in terms of setting some of the timeline, is being able to develop these new regulatory frameworks. But I don't see it as an ultimate impediment to the overall mission space of urban air mobility. You showed many examples from civil aviation. What priority does innovation and disruption in military aviation have for Airbus? Actually, a very high one. We are, as probably many of you know, the leading defense company in Europe. So the European governments rely on us for Eurofighter, for the A400M transport aircraft, and for many space assets that we develop for them. It's a bit easier in a forum like this to focus on the civil side. And the bulk of our business does come from large commercial aircraft and the civil helicopter and the commercial satellite business. I think that innovation in the military space it's a single customer business in some sense, or at least a small handful of customers that tend to be rather monolithic. So I think the dynamics of that industry are a bit different, but I think that it is likewise poised for disruption. And I think that the military customers are increasingly recognizing the fact that they also are facing a spectrum of threats globally and a spectrum of countermeasures to some of our high-value assets globally that are at a different clock speed and at a different cost structure than the one that we operate in. So I think many of the lessons and many of the main points, the main themes that I made in my presentation are fully applicable in the military domain. Just the dynamics of the market are a little bit different. All right, so I do one last one. Do you think Airbus cannibalizes itself by trying to find innovation outside the company rather than developing it on its own? And I think this is a nice question to end on because I think it neatly depicts one of the main points that I tried to make. I think it's the fact that the notion of captive innovation and of a captive workforce and monopoly over ideas, I think that notion is very rapidly becoming antiquated. So this is one of the reasons that openness and engaging an external ecosystem, a diverse external ecosystem, is essential both as a talent recruitment pipeline for us and a recognition of the fact that we will probably never again be fully successful as a completely vertically integrated player in many of the domains that we operate in, just because the investment levels that you see in electrical technologies from automotive, in digital technologies from consumer, and in manufacturing technologies from who knows so far. I think we will never probably again own all of those domains and own the entire technology base on which we create our products. And I think we should recognize that and develop an innovation ecosystem and an innovation framework that is porous and that accepts this fact and exploits it to maximum effect. So this is what we've tried to do, and this is what I tried to describe to you, and some of the things that are coming out of it. So with that, I thank you for your time. I thank you very much for your questions, and I look forward to chatting with you off stage.
Thank you very much, Paul, for that insightful talk and a view into the Airbus disruptive plan for the future. Just want to let everybody know that there is coffee available now until 9:30, and I hope you take advantage of this time to meet and have discussions with folks that are here at the conference. Today, we will have two Forum 360 programs in the Grand Ballroom 1. Our 9:30 a.m. session will be the evolving culture of aviation, and at 2 p.m. session, we look at supersonic transport. Please refer to your programs for additional information on each session. Also today, our Demand for the Unmanned Symposium starts this morning at 9:30 and runs through tomorrow. If you want to learn more about the future of unmanned aerial systems and autonomous systems, you'll find plenty of interesting sessions to attend. For more details, check your programs. At noon today, there'll be a lunch and learn in the Grand Ballroom 1 for young professionals attendees on your next move, how to build a strong foundation for a long-term career success. Also, please join us this evening in the reception hall for a reception in the exhibition hall tonight at 6:30. This will be a great time to meet fellows, attendees, and visit our over 40 exhibitors. During tonight's reception, visit the AIAA Pavilion and its author signing event, where you can meet Leland Nicolai, author of Lessons Learned, A Guide to Improved Aircraft Design and Fundamentals of Aircraft and Airship Design. He'll be signing copies of his work from 6:30 to 8 p.m. this evening. Also, while visiting the exposition tonight, please don't forget to register for the UAS giveaway. We'll draw the name of lucky winners on Thursday. Thank you very much for attending this morning, and have a great day today here at AIAA Aviation 2017. Thank you.